and then we start. Okay, let's wait until 1:04. Okay, then I stop sharing the screen. And I guess we can slowly start. So good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I will introduce to you just now all the people that you see in our panel this afternoon. And let me start by introducing our speaker, Dr. Cora Dvorkin. And we are very grateful that she's with us today from Harvard. And in a minute, I will ask Amanda Veltman to do the proper introduction of the speaker. So on the panel, as I just mentioned, is also Professor Amanda Veltman from UCT. And she suggested to invite Cora Dvorkin to this colloquium today. So she will start by introducing the speaker just now. Next to Amanda is also Professor Yingxue Ma from UKZN, and I asked Yingxue to be so kind to moderate the question session at the end of after the talk, so that the speaker doesn't have to multitask in checking various channels while she speaks. And also on the panel is Dr. Sinaisky, who I always ask to be the backup plan, and he every time kindly agrees, just in case my internet dies or the electricity goes off or something. He has all the rights to keep going with the webinar. So again, thank you very much for being with us today. And Amanda, can I ask you now to please introduce the speaker?
With pleasure. So today we're delighted to be hosting Professor Cora Dvorkin from Harvard University. She's going to talk to us about some of the advances that her and her group are making in cosmology. We're hoping that we get to host her very, very soon in person. But until then, we have a lucky opportunity to take advantage of the pandemic to learn about her work from a distance. Just a little brief snippets from her bio. Professor Dvorkin has a very illustrious career so far. Her PhD was from the Department of Physics at U Chicago, where she, I think, began a reasonably long stretch of winning awards. She trained thereafter at the Institute for Advanced Study in Princeton, eventually at Harvard, and now she's a permanent faculty member at Harvard. She's won a number of fellowships and grant awards. Possibly the most recent and exciting is an award to use AI to connect fundamental physics and astrophysics. So that's a very exciting thing that the NSF is building, an organization that the NSF is building across multiple institutes, including Harvard. And I'm hoping that at some point during the cosmology talk, we'll hear a little bit about what's planned. If not, we're going to have to invite you again. But Cora is also one of the leaders of the inflation group for the CMBS4 experiment. And so she is one of those very valuable theorists who has her hands properly deep in the data. So without further ado, I bring you Professor Cora Dvorkin.
Thank you very much. Let me share my screen. Perfect.
Perfect.
Put
Great.
this down. Excellent. Do you all see my screen?
Yes.
Yes.
Very well. Thank you.
Great. Okay. So let's get started. Well, first of all, thank you very much for the invitation. And thank you very much, Amanda, for this very nice introduction. And I hope everyone is doing well in these very difficult times that we are living. So as Amanda said, I'm Cora Dvorkin. I'm an associate professor at the physics department at Harvard. And today I will be talking about how we are trying to shed light on the dark sector using information coming from cosmological observables. In particular, I will be talking about observables at small scales. So, whoops. Here is a roadmap of the talk. I will spend some time setting up a very simple model of the universe that works beautifully, but I will tell you how we still have fundamental physics questions that remain unanswered. In particular, the focus of my talk will be the particle nature of dark matter. I decided to divide my talk in two. I will be telling you about how we can use gravitational lensing to probe dark matter at small scales. In the first part, I will start by a promising technique that I have been working on over the past years, a statistical measurement of dark matter substructure using strong gravitational lensing. And then I will be presenting some recent machine learning results, as Amanda mentioned, that we had with my group on directly detecting dark matter clumps at small scales. And the take-home message, as you will see, will be that we are gathering a large amount of data now, and a lot more will come. And this data can really help us inform, shed light on the nature of dark matter. The vast majority of this talk will be on how we can extract useful information to make progress on this fundamental question in suitable ways. And I will wrap up at the end with some concluding thoughts. So let's get started. This line of time here that I like to show represents 13.8 billion years of the universe. As we know, the universe began as a hot and dense plasma of particles in thermal equilibrium. It expanded and cooled, and many physical processes happened along the way. Some of them we know very well, some of them we still have question marks on it. We know that, for example, around 400,000 years after the Big Bang, the universe reached a temperature that was cool enough to have protons and electrons combine into hydrogen atoms. This period is known as recombination, although I always say it should be called combination since it's the first time this happened. Anyway, since then, the universe became mainly transparent to CMB photons, and photons mainly come toward us free streaming until about 500 million years after the Big Bang, when the first stars and quasars reionized the universe in a period that we know as reionization, and about 6% of these photons rescatter. This 6% is the latest number from the Planck satellite. And today we observe these photons at microwave frequencies and at a temperature of 2.7 Kelvin, which is 270 degrees Celsius below zero, very cold temperatures. So we have a standard model of cosmology known as lambda CDM, and this model has been extremely successful on cosmological scales among a wide array of different experiments. We have CMB temperature, CMB polarization, and different observables. We have clustering of matter, for example, that measures the matter power spectrum, or measurements of the expansion history of the universe. And so here I'm showing you the matter power spectrum as a function of wave number. Here, small scales are to the right, large scales are to the left. And you can see this is a log-log plot, and it covers 4 orders of magnitude in each of these axes. The black line here shows you the predictions of our lambda CDM standard model of cosmology, and each of these data points is a measurement interpreted within the context of this model as a measurement of the matter power spectrum. So for example, if you look at the blue and orange points, those points come from measurements of temperature and polarization of CMB by the Planck satellite in this case. The green points show that the CMB photons come toward us, so that as the CMB photons come toward us, they transverse the large scale structure as they move in and out of the gravitational potential associated with this large scale structure, and they have their photon path deflected. This gives rise to gravitational lensing that alters the patterns that we see in the CMB. There is a similar effect shown in yellow here that shows the deflection of light paths, in this case, not the CMB photons, but of photons emitted by galaxies. And finally, the red and purple dots over here show us the clustering of galaxies and intergalactic hydrogen as measured, in this case, by the Sloan Digital Sky Survey. So what's interesting about this figure is that it's spanning 14 billion years of history. It's spanning 4 orders of magnitude in length scales and a wide variety of cosmological probes. And we can see how lambda CDM model fits them all beautifully. So this is a huge success. Now let's move on to smaller scales. And this is a figure that I took from Andrei Kravtsov paper in 2009. And so here, what the point that I'm trying to make is that because of our knowledge of structure formation and the fact that it's hierarchical, we do expect an abundance of structure within dark matter halos. In particular, in the cold dark matter scenario, for example, we expect a high abundance of substructure compared to other dark matter theories. And we see the predicted dark matter density for a Milky Way size halo in this case, and we can see that there is structure within the halo, so clearly it's not empty. But it is unclear how to tie these observations to a dark matter theory, and I will be talking about this today. So I will be focusing on the CDM part of our lambda CDM model. And I will tell you about some of the research that we have been doing with my group at Harvard to provide an understanding of the question, what is the particle nature of dark matter, which constitutes approximately 84% of all the matter in the universe. So 84% of all the matter in the universe is in the form of dark matter, and we still don't know what it is. In the past few decades, we have measured the large-scale structure of the universe very accurately with many different probes, CMB, Lyman alpha forest, weak lensing, etc., etc. And this has allowed us to put precision level limits, as I showed you before, on different kinds of dark matter scenarios. But on smaller scales, there is a lot of structure that it is not well understood or as well understood. Furthermore, many dark matter scenarios that agree at large scales by construction show differences at small scales. So small scales provide fertile grounds for testing these different scenarios. And we will be using the smallest scales to either falsify or corroborate the CDM paradigm, as I will show you just now. So in particular, I will talk about probing dark matter substructure via strong gravitational lensing, and I will define those things in a bit. I will start by telling you about a promising technique that we have been working on with my group over the past years based on substructure statistics. So our goal is to map the distribution of dark matter on small scales in halos of galaxies. And our tool for this will be strong gravitational lensing. So let me give you here a review in one slide of gravitational lensing. So we will have a background source at some high redshift here, which will be a galaxy in this case, and there will be a foreground galaxy here, and this foreground galaxy will deflect the light because of gravity. So from our perspective, we will see extended arcs over here. You can see extended arcs. So the idea will be to use these images to see if the lensing galaxy is clumpy or smooth. That's the main idea. This is the lens equation that I'm showing over here, where you can map an image back to the source plane by a deflection angle field, which is the gradient of the gravitational potential of the main mass acting as a lens. So the idea that has been suggested about 20 years ago by Mao and Schneider is that substructure in the halos will locally perturb lens images. So by looking at the residual between the image predicted by modeling the lens as a smooth mass and what is actually observed, we can infer the presence of subhalos. And I like to say that the advantage of this method relative to other methods for detecting dark matter that, for example, I have been working on over many years, is that we do not need to assume a coupling between the standard model and the dark matter, in contrast, for example, to direct and indirect detection experiments or colliders. And so in this sense, we are model independent. And another main advantage of the technique I will tell you about, as you will see, is that we will be focusing on the lowest mass of halos. And So we can hope, because of this, to minimize baryonic feedback. So the lens galaxy will have small scale structure, and this will cause a small deflection as the light from the source crosses the lens. And if you don't have superpowers in your eyes, you will not be able to see any difference between these unperturbed images that I'm showing here. Probably you don't see any differences. These are the image residuals once we subtract a smooth model of the lens. And here we are talking about a percent effect on the surface brightness of this lens galaxy. You can see here the numbers. This is a percent effect on the surface brightness map. And these variations are caused by having substructure in the lens galaxy. So we can individually go and detect the higher mass subhalos, and this has been done in many works in the literature. However, there is a much more numerous population of low mass subhalos, and by this, for purposes of this talk, I mean less than 10 to the 8 solar masses. And this may be statistically detected by their collective perturbation on images. Yasser Hessave and collaborators pointed this out a few years ago in a very nice paper. And so the key question that we asked with my group is, if we actually go and measure the power spectrum, what can we learn about low mass subhalos? And in particular, what can we learn about the nature of dark matter? And this would be very promising if we could learn something, because it can measure directly the dark side of galaxies. So let me start by telling you a formalism that we built in a paper with Ana Diaz-Rivero, my PhD student at Harvard, who actually recently graduated, and Francis Yancy Racine, who was a former postdoc at Harvard, who is now a professor at University of New Mexico. So we developed a general formalism to study, in principle, the endpoint correlation function of the convergence field, and we started from the power spectrum. It's the easiest. So if we have a lot of substructure, the perturbations will look very close to Gaussian, right? The central limit theorem will kick in, and most of the information should be in the power spectrum. So we model the convergence field, and by the way, when I say convergence field, I mean nothing more and nothing less than the adimensional surface mass density. We model it as a substructure component on top of a smoothly varying background density profile of the host. And here the convergence field of the substructure depends on the substructure position, the mass, and intrinsic properties. These QIs are intrinsic properties of the subhalos that might determine the density profile. For example, its truncation radius in the case of the truncated NFW profile. So here what we propose is a change of language and moving away from talking about subhalos, and instead we propose to talk about the correlation function of the projected density field. So in this sense, we don't need to define what a subhalo is and what it is not, as it is generally done in the literature. So we start from first principles, and this has been actually done for the large scale structure a long time ago. And since when I started this work, I was more familiar with this area, I borrowed their terminology. So here we are essentially applying the same kind of philosophy, but for smaller scales. So I will be describing the power spectrum in terms of a one subhalo term instead of the one halo term, and the two subhalo term instead of the two halo term. So the one subhalo term arises from ensemble averaging over the spatial distribution of a single subhalo, and the two subhalo term arises from averaging over pairs of distinct subhalos. And here, as you can see, we are taking integrals over the probability, over different probabilities of the mass, the intrinsic properties, the spatial distribution within the host. So here's our power spectrum. This is our result. You can see that the power spectrum is mainly described by three quantities. We will see this now. At low K over here, we will have a plateau, a constant amplitude. And here, basically, we can understand this because we are probing scales that are much larger than any subhalo, okay? This low K limit corresponds to very large scales. So at these very large scales, all the subhalos are essentially point masses, and the Fourier transform of that is white noise. So the amplitude, so we see a plateau. And the amplitude depends on average abundance of substructure as well as different mass moments. As we move to small scales to the right, we turn over. And this turnover corresponds to the truncation radius given by tidal interactions of the largest subhalos in the lens galaxy. And if we keep moving to the right to smaller scales, we can reach an asymptotic regime where the power spectrum asymptotes to a constant power law, which for an NFW profile that describes well the cold dark matter scenario, it goes as K to the -4. Now, if we have a non-trivial dark matter scenario, and by this I mean any dark matter scenario that is not CDM, the density profile will change. A scenario, for example, that has been well studied in the literature, proposed at the time to solve some of the discrepancies seen between observations and simulations, is the so-called ACDM scenario, strongly interacting dark matter. And it has been shown that this scenario gives rise to a chord profile, as we can see in this figure here, where you see this is the density profile as a function of radius. The chord profile in green corresponds to the ACDM scenario, and in blue, I'm showing you the truncated NFW profile that describes well CDM. Now we can see that at small scales, we actually change the slope, which reflects the fact that ACDM subhalos inner density profile looks different. Now it goes as 1 over K to the 8, and we can show this analytically. So, there is a difference between 1 over K to the 4 and 1 over K to the 8. And this difference in principle can help us distinguish between different dark matter scenarios. However, note that the largest differences correspond to very, very small scales. So these correspond to 1 to 100 parsecs, which are scales difficult to reach in the near future. So we were very happy with this result, but in principle, this is telling us that in theory, we have a way to differentiate, but it will be very difficult with current or near coming experiments. However, we realized later on by looking at simulations that we could use the information at larger and more accessible scales by adding redshift information. And this is what I will show you now. So once we had our formalism built and before looking into the data, we decided to test it in simulations. And for this, we used Mark Vogelsberger simulations. Mark is a professor at MIT. At the point, it was convenient that he was, very close to us. Now it's the same, but we took his simulations in particular for a CDM case over here and a non-CDM scenario, what I will call our exotic dark matter scenario, which is in this case, a case with strong interacting dark matter plus a cutoff in the initial power spectrum. You can see here a snapshot of these simulations where it is already clear by eye the lack of small scale power seen in the exotic dark matter scenario compared to the CDM scenario. You can already see it by eye. Okay, so here are our results. First, we saw that our predictions match what we observe in the simulations. So equipped with this, we started investigating the differences between different dark matter scenarios. Let's start with the CDM case. So here the different lines, the different colors correspond to different redshifts, okay? So as I go up here, I approach redshift 0. And as we approach redshift 0, we expect more subhalos to be accreted into the host halos, implying that the amplitude of the power spectrum will increase, which is what we see. Now let's look at this ACDM scenario with a cutoff. So here, mass loss due to tidal interaction becomes important. This gives on average a reduction of the effective subhalo mass between redshift of 0.5 and 0, leading to a net transfer of power from larger to smaller scales in the power spectrum. Furthermore, the much larger total number of subhalos in the CDM case also means that the 2 subhalo term makes a non-negligible contribution at redshift equals 0, which tends to increase the magnitude of the redshift evolution in this case. In contrast, this exotic dark matter scenario does not get a significant 2 subhalo contribution at redshift equals 0. Now, Now, another important aspect of the redshift evolution is the difference in the power spectrum slope for wave numbers greater than about 2 inverse kiloparsecs, which are scales that are actually within the reach in the near future by the Hubble Space Telescope, HST or ALMA. So this exotic dark matter scenario simulation has a lower central density of subhalos, as we saw, making it more susceptible to tidal effects and mass loss. And we indeed find that the substructure mass fraction in subhalos with masses less than 10 to the 7 to 10 to the 8 solar masses grows more rapidly between redshift of 0.5 and 0 compared to CDM. So you can see that this here grows more rapidly than this part over here. So this can potentially be a very powerful probe at low mass dark matter clumps. So again, we can, using the redshift information and comparing different redshifts, we can access larger scales that are accessible by current and near future experiments and use these to distinguish different dark matter scenarios. So I borrowed this slide from my former student, I should say, because she just graduated, Ana Diaz Rivero, because I think it is a neat diagram that describes the bridge that we are doing here between theory and observation. So the reason why we like the convergence power spectrum so much is that it gives us a way of mapping what we have, a strong lens image, to what we want, a dark matter theory. And the way that this is done is by the fact that the convergence power spectrum can relate a length scale, deflection vectors on the lens plane, to a mass scale, which is given by the halo and subhalo mass function, which actually is what dark matter theories give us. So the convergence power spectrum is a nice bridge between the two sides of this diagram, the observations and the theory. So we saw that the convergence power spectrum of subhalos within lensing galaxies is a promising observable to study dark matter. However, actually the distances involved in strong lensing systems are vast, and we expect the relevant volume to contain line of sight halos that are not associated with the main lens. By the way, in this talk, I will be using line of sight halo, perturber, or interloper, all as synonyms, okay? So recently, in a paper led by 2 of my graduate students, Chan Sengul and Arthur Tsang, we developed a formalism to calculate the effect of line of sight halos as an effective convergence power spectrum. And now, instead of having a single lens plane at some redshift, we have any number of lens planes, as I'm depicting here just for illustrative purposes. So instead of using the vanilla lens equation, now we have a recursive lens equation, which couples the angular deflections of successive lens planes of all these interlopers along the line of sight. And so by assuming that the perturbations due to the line of sight halos are small, we show that they can be projected onto the main lens plane as effective subhalos. So we define an effective convergence modifying the internal properties of the halos, and we could then write an expression for the interloper power spectrum. And the features of this power spectrum are very similar to the ones I showed you before, so we don't have to go into them. We have it, but let's take a look at the differences. So here we have a convergence profile, which with a rescale scale radius, as I'm showing here, a mass distribution Now, here that not only depends on the mass, but it also depends on the comoving distance and a probability distribution of intrinsic properties, which is now also a function of distance. And finally, we have now a completely new ingredient, which is this selection function that tells you how to weight interlopers depending on whether they are foreground or background. So we tested our formalism by simulating lensing systems using the full multiplane lens equation and found excellent agreement with our analytical predictions. And I'm showing you here a test of this formalism for a particular set of parameters. I don't need to describe the set of parameters, but so here, basically, we saw a very good agreement, and we saw that the line of sight halo contribution to the power spectrum is at least 7 times greater than that of subhalos for the source redshift and lens redshift that we were considering. Here in reddish colors over here, we see interlopers plus subhalos, and in green, we see subhalos. But of course, this is just one particular case that we consider. From here, we cannot make a global statement, and we want to make a global statement. But the problem is that this will depend on how many interlopers versus how many subhalos there are. So we showed how the relative contribution of line of sight halos and subhalos depends on the source and lens redshift. You can see here the lens redshift, and I'm cutting this, but you can see the source redshift over here, as well as the assumed halo and subhalo mass functions. And to understand this, here we fix the halo mass function and we vary the amplitude of the subhalo mass function. So here, this F sub, you can think about it as the amplitude of the subhalo mass function. And here, redder colors show that the interlopers dominate, and bluer colors show that the subhalos dominate. Pretty intuitively, we see that as we increase the amount of substructures, the colors go from red to blue over here. The question is, which of these 3 panels we are observing in practice, right? We don't know exactly what this F sub parameter is, but people place upper limits based on measurements of different systems using gravitational imaging. And we see that having a substructure fraction of 2% is very unlikely for the mass scales we are considering here. It is much more likely that we are in a scenario like this one over here, where the F sub is smaller than 1%. Meaning that the interlopers are dominating. And this is good news in that a measurement of the power spectrum may be measuring the halo mass function and not the subhalo mass function. So to be more specific, we overlaid points that correspond to Bell's family and Slack's family over here. And these are well-known families of galaxy-galaxy lensing. These are 2 high-quality sets of lensing images. And in particular, these are sets that have been used to place constraints on dark matter. And we can see that for both sets, for a fraction of substructure that we think is more realistic based on the literature, they are dominated by the halo mass function. So for current images used right now to put constraints on dark matter, we think, it is much more likely that people are probing the halo mass function and not the subhalo mass function. So the fact that under many lensing configurations and reasonable subhalo population assumptions, the interloper contribution dominates the signal can be good news for the capacity of strong gravitational lenses to constrain the particle nature of dark matter. The amplitude of the convergence power spectrum can essentially be tied back to a mass function. So in order to translate a power spectrum amplitude to dark matter theory, it is paramount to understand whether the subhalos or interlopers are the dominant contribution to the power spectrum. Otherwise, we could obtain bias constraints or on dark matter or falsify paradigms that are actually not really falsified. So the subhalo mass function is very hard to pin down. It depends, as we saw, on the host halo mass and evolves with Redshift. And how it is affected by subhalos traveling within the host dark matter halo, as well as due to baryons in the host, remains actually an open problem in the literature. In comparison, halos that are only subject to large-scale tidal fields have relatively calmer lives, and their evolution is better understood. Therefore, we think that having a window into the smallest dark matter scales in the universe without relying on subhalos can actually make gravitational lensing a much more powerful and reliable probe of dark matter. Now, in terms of the road ahead, the Vera Rubin Observatory, formerly known as LSST, will discover tens of thousands of lensed galaxies. At the moment, we have tens of galaxies. We will have tens of thousands of lensed galaxies. And this vast increase in sample sizes will provide much stronger constraints on dark matter. And so with a group of cosmologists working on dark matter, we submitted last year a paper that points out the advances that we will be able to make in the dark matter frontier once the Vera Rubin Observatory has its first light. And now the Vera Rubin Observatory, which has been historically a dark energy survey, has added dark matter science to their formal agenda. So we were very happy about that. Okay, so let me now talk about how direct detection is done to resolve individual massive perturbers before telling you about our machine learning results. So the quintessential method for what I call here direct detection of dark matter substructure is gravitational imaging. The idea is the same as what it was proposed 20 years ago by Mao and Schneider. If you have some dark clump lying close to an emission, there might be some visible distortion that you can try to reconstruct. So people start with the data, a strongly lensed image. By the way, I'm taking this from a paper by Veghetti et al., a Nature paper in 2012. So people start with the data, and the prerequisite is to model the smooth component of the lens, assume that the object doing the lensing has no clamp, so you model it by a smooth component, and you also need to reconstruct the source. And so once you have these two components, you can come up with a smooth model image that I'm showing, that they are showing here, okay? So you can take the difference between the actual image and your smooth model and get your image residuals. And the idea is to minimize these residuals by placing small potential corrections. So you play with small potential corrections in order to minimize this residual. And then you can get the potential corrections and relate them, the ones that minimize the residual, and relate them to the reconstructed surface mass density. And these overdensities, if significant, will be pointing to new dark matter subhalos. For example, in this paper, they claim a 12 sigma detection of a subhalo that we can see by eye here. Of course, you could not see it by eye here, but after doing all this procedure, you can see a clamp here, and they claim a 12 sigma detection of this subhalo. In this particular case, it was a subhalo that they claim had 10 to the 8 solar masses. So direct detection of substructure is computationally very expensive. It takes weeks to months to analyze each system, and most of the time one gets null detections. And lens modeling is not straightforward, and the additional post-processing makes the process very slow. To put into context how hard this problem is, so far, 2 detections were claimed using this method in about 30 images analyzed so far. So up to now, the pool of lens images has been small, but in the next few years, as I told you, we will expect this number to increase by many orders of magnitude. We expect tens of thousands of lens galaxies. So what motivated us, together with Ana Díaz Rivero, was the following question. Can we automate a procedure like direct detection using convolutional neural networks, making this process much faster, avoiding the step of macro modeling? So in this case, the promising candidates can go into this much more detailed analysis pipeline that we saw before, whereas the vast majority that don't have substructure don't have to see all this time and resources spent on them just to get a null detection. And if you understand the sensitivity of your machine learning model well enough, you can still combine detections and non-detections to put constraints on dark matter. So the non-detections, I want to emphasize, are important to combine them into constraints on dark matter. So the costly step of our procedure was to simulate high fidelity, high quality, strong lens images. And to do so, we used a publicly available code. It's a beautiful code called Lenstronomy, developed by Simon Bierer, who is now a postdoc at Stanford. This is an example of the individual components that went onto simulating the final image. We vary the macro model and the source together with the subhalo population. In every image, we had a different subhalo population and a different macro model, a different source. There are many degeneracies between these parameters, so it was not trivial at all that this network could learn. For the source, we model it as a superposition of different clumps. We vary the ellipticity and the position of the host relative to the source. For the images with substructure, some of them didn't have substructure. For the images with substructure, we modeled them as NFW profiles, and we took the subhalo mass function to be a power law. We then convolved the image with a Gaussian PSF, point spread function, with a width of 0.07 arc seconds to make it similar to HST, and we added Poisson noise. And we also tested here, you can see these different L's. We tested for correlated noise. Here L is the correlation length. So for this, we used the Gaussian process to vary the correlation length in the correlated noise. And we think that the noise will be correlated because HST images, for example, might have correlations due to drizzling, just as an example. So we turned the problem into a binary classification task, and we asked the question, for what mass ranges of substructure is the network able to recognize the lens as having substructure versus not having any? And the expectation is that for very low masses, the network will not be able to detect anything, but if it is massive enough, the network will be able to detect it, just analogous to direct detection methods that I showed you before. So we first simulated a subhalo population with one subhalo just to test the network. On the left panel, the noise is uncorrelated, and in the right, we vary the correlation scale. So for low, and so here I'm showing you the accuracy versus the mass of the subhalos, and this is the macro model. So for low values of the subhalo mass, the accuracy lies well below 50%. This may sound strange because we are having a classification problem, so you would expect at minimum to have 50% accuracy, just if complete, just by complete randomness, you would get 50%. But the fact that we are getting results below 50% reflects the fact that to the network, the images with low mass subhalos are indistinguishable from macro-only model. And now then we see that for 5 × 10⁹ solar masses and above, the accuracy is better than 75%. And of course, it gets better when the noise is reduced. And unsurprisingly, the accuracy takes a hit when you add correlated noise because it can mimic the signature of a perturbation caused by a small subhalo. You don't know if it's a small subhalo or the noise having some correlation. Then instead, we tried both fixing the number of subhalos and the fraction of mass in substructure. And this is what I'm showing you here as N sub bound and F sub bound. And these two cases gave very similar results. Basically, both are telling us that our network is sensitive to a massive perturber, analogously to direct detection methods. And we again find that subhalos have to be above 5 × 10⁹ solar masses in order to have a 75% accuracy or better. And this is actually comparable to the numbers cited in the literature for real detections. Masses cited actually tend to be lower because they do not take into account, in general, projections from 3D to 2D. So in this work, we show that small-scale substructure can be inferred directly from astrophysical images by using convolutional neural networks without doing any intermediate modeling of the lens galaxy or any intermediate modeling of the source as well. And we also saw that with this method, it takes much less than a second to analyze a system versus weeks to months that it takes in traditional analysis. And so we were very excited about this. And we also noted in this paper that this was the first proof of concept that we were making, that we didn't vary the architecture, we didn't optimize for the machine learning method that we were using. So just as a first proof of concept, we saw that this was actually possible. So we then moved on to actually use the different architecture. And this is work that I have done together with, that we have done with Ana Diaz-Rivero and together with my postdoc, Brian Osdieck at Harvard. We moved on to use UNets, which is, are a network well known for its success on image segmentation. Image segmentation is the problem of taking an image and trying to understand what are the individual components that make up this image. Here, we teach the network to reconstruct the convergence field by classifying every single pixel in the image as belonging to the background, the main lens, or to one of 9 different subhalo mass classes. And we chose these 9 different subhalo mass classes to be beams in mass. The network takes as an input a strong lens image. And this is what we want the network to predict over here. So we can see that most of the pixels over here are in the background. There is the main lens. And in this case, there is a very small subhalo over here with a mass of 10 to the 6 solar masses. What the network outputs is these 11 panels that you see over here. And for each class, it outputs what is the probability that you have that class versus not having that class. So bluer colors correspond to higher probability and redder colors correspond to lower to 0 probabilities. So you can see that the network is very confident on what it identifies as background. Here you see that the background, this is the background, and it actually sees that the background is mainly blue, is very confident to what it identifies by main lens. This is the main lens, and the main lens, except for some edge effects, the main lens is really very confident that this is the main lens. But surprisingly, it is also very certain that this corresponds to a very small subhalo over here, 10 to the 6 solar mass subhalo. You can see that there is also a bit of artifact here. You see these artifacts over here that creates a fake pixel with a mass of a particular value, of different values as I go on the different panels. But in general, we were extremely surprised that the network was doing so well, even for very, very low dark matter clamps. I mean, lower than what we have seen before. As a disclaimer, there is no noise in this example. So then we moved on to add noise. And we looked at the problem a bit more statistically by studying the confusion matrix. So here, each column is normalized to 1, and it gives the pixel probability. Okay, this is predicted versus target for a case with no noise and a case with 1% noise that we think resembles quite well the noise, the level of noise seen by HST. So let's start looking at this confusion matrix. The fact that it's diagonal tells you already that the accuracy is very good. Most of the pixels are predicted to be in their true class. This is because it's diagonal. This is what you expect. You see some off diagonal elements, but most of them correspond to the adjacent beam. And that makes sense because the masses of subhalos are continuous, whereas we are artificially choosing discrete mass beams. So there are edge effects over here. You see these edge effects over here, but in general, it's pretty diagonal. Also, for the very low masses, you can see that there are quite a few pixels that get confused with the background or the main lens. And this makes sense because we are looking at these very teeny tiny perturbations. Now, when we add noise over here, which again is noise that we chose to be HST realistic noise, we see that now the network struggles to find the low mass subhalos. Over here, it's struggling to find them. And this is because the level of noise is above the pixel brightness changes due to the presence of these subhalos. So we could see that we could map perfectly well the pixel brightness changes due to subhalos of the masses that we don't see to the level of noise. So the level of when the pixel mass brightness starts being above the level of noise that we have is exactly when our confusion matrix shows us that we start predicting the corresponding mass. So we understand this quite well. We understand how this network is working. So we also saw that the network can find many subhalos. We trained the network with one subhalo. We saw that it can find many subhalos of different masses. We saw that it actually can also find not only one lens. We trained it with one lens, but we saw that it can find, if we have a problem with two lenses, it also predicts these two lenses. So it goes way out of the domain of training. So what we decided to do, so for example, this is an example that I took where we see the target and we see the prediction and the different colors correspond to different masses. Some of them it doesn't predict, but in general, this is just some example. It predicts them quite well. So what we decided to do is to combine many images to place constraints on the subhalo mass function instead of having to do some additional post-processing. And we find that if we combine, these are our results. So if we combine order tens of images, the subhalo, we can get errors on the slope of the subhalo mass function of about 10%. Which is already quite good. If we increase the number of images, the error bars, of course, decrease, as you may imagine. If we combine 1,000 images, we get errors of 1% on the slope of the subhalo mass function. And this is true for images with and without noise. So this is quite exciting. Oops. Okay, so I arrived here to my final slide. And I will leave you now with some concluding thoughts. So I showed you how we can find important clues about dark matter physics on small scales. We saw that the convergence power spectrum relates, it's a nice bridge that can relate length scales, the observable, to mass scales, which are given by dark matter theories. And so this is the connection that we want to make if we are going to use observations in order to put constraints on the particle nature of dark matter, which is always the goal that we have in the back of our mind. I also showed you how we can use gravitational lensing to probe an untested regime of the CDM scenario. And by this, I mean kiloparsec scales. We then saw also that the dominance of interlopers in strong lensing systems opens up actually a promising avenue in the search for dark matter. Now we see that in these vast distances between us and the lens, it is much more likely that these vast distances are dominated by interlopers than by subhalos. And this dominance of interlopers actually may be good news for the search of the particle nature of dark matter. And finally, I showed you our latest results on machine learning applied to the strong lensing problem. And I showed you how machine learning can accelerate by many orders of magnitude direct detection efforts, and by circumventing the step of lens modeling. And not only it accelerates it, but it also can provide results that are very accurate. Finally, more generally, I want to say that this coming decade will bring a wealth of new data, new cosmological and astrophysical data, and these data are different and complementary to each other. And so using the different data sets, but also using the complementarity between different data sets can help us advance our incomplete understanding of the universe. With my group, we not only study strong lensing. I talked here about strong lensing as a way to constraining dark matter at small scales, but we also look at other probes, for example, 21 centimeter. We look at the large scale structure. We look at the CMB on larger scales. And I think that from the complementarity of these different probes, we will hopefully shed light on the dark sector soon. Thank you.